All right, ladies and gentlemen, we're going to continue our discussion of chapter 3. We have two new words. They are found here and here. Enantiomers and Diastereomers. Enantiomers, Diastereomers. Right here. Enantiomers are chiral. They have to be chiral. Each molecule in a pair of enantiomers has to be chiral. That means it has to be handed. Like your right hand is different than your left hand, right? And they have to be mirror images of each other. So here's how I like to demonstrate it perfectly. We got the word chiral might be new to some of you. Chiral means it's handed. So this object is handed. My right hand is handed. Do you know how I know? Because it's different than my left hand, which is related. They're mirror images of each other. And they're not the same because when I try to put them on top of each other, I got thumbs on pinkies and pinkies on thumbs. They don't match. Now, if you try to match them this way, well, I mean, the top of this molecule's bottom area, you got to have them lined up, and the parts don't match, so they're mirror images of each other. So chiral molecules are handed, okay? Handed and chiral are synonymous. Enantiomers are a pair of chiral molecules that are related in that they are mirror images of each other. Okay? Your right hand, left hand. Your right ear, your left ear. But your right ear is not an enantiomer of your left hand, is it? They don't have the same parts at all. You gotta have the same atoms and the same order of attachment. We're talking molecules now. So basically, the end of the name has to be identical with all the groups and the same carbons, okay? And every stereocenter will be the opposite. I mean, what's the mirror image of a right hand? I don't need to do a demo, right? It's a left hand. What's the mirror image of a R stereocenter? An S stereocenter. Okay, so I think we're ready to start. In diastereomers, I think it's best to introduce those when they come up. We're going to be starting with enantiomers, so let's just carry on with that. So this is very much, the way this is laid out is the strategy to answer the question on the test. Because on the test, it just says this. I'll convert this to a test question. Draw all possible isomers of, and I will just give you this part of the name, starting with the 3 here. 3,5-diiodo, 5-cyclopentyl octane. I will just ask you to draw every isomer of it. And these steps here guarantee that you will have every isomer of it drawn. So you can use these steps or use my videos because I've done about 6 of these on video. And it's a good 18-point question on a test. Next test. So when I have to draw a molecule, I start with the octane in this case, 2, 4, 6, 8. Carbon 5 has a stereocenter, 2, 4, 6, 8, and carbon 3 has a stereocenter. There's 3. And I know that from the name. It says 3R5S. So what are the things on 3? Well, there's an iodo on 3 and another one on 5. And a cyclopentyl on 5. And you better show me the 4th substituent on stereocenter carbon number 3. Because right now I got a stick there, and that means there's a methyl. There's no methyl in the name. So what's at the end of that stick? H. Okay, and our strategy for doing R and S is always the same. Yeah, I want R, right? So if I do my 1, 2, 3, 4 and connect them, and that ends up being the one I want, then the 4 is going to be on a dash, right? But I didn't get the one I want. When I connect 1, 2, and 3 here, it's F. So how do I make sure it's R? Exactly, put a wedge on 4. And then go adjacent for a dash. We'll go iodine is adjacent for short, and there you go. And new story over here, 1 for iodo. This time the 2 is the cyclo because it's got 2 bonds to C, and this one does not. That only has 1 bond to C. And 4. And this is S already, so 4 is going to be on a dash. And adjacent for a wedge. There you go. And now 1, 2, 3 gives the wrong answer. F is, sorry. No, it's the right answer. Yes, right answer. That was the wrong answer, the first one. Congratulations, you drew 3R, 5S, 3,5-diiodo, 5-cyclopentyl octane. Okay. Draw its mirror image. So we have to get good at drawing mirror images. You do not need to have any spatial gifts like this. Being able to visualize things spatially, you do not have to. Here's what I'm going to do. I'm going to just draw an imaginary mirror. Mirror on the wall. I'll draw it right here. Okay. And the same distance from the mirror will be carbon 8 of this octane. Goes down, comes up, and the dash is going away from the mirror and down. And when it ends, the wedge is towards the mirror and down. See how I'm describing everything relative to the mirror. And then I have this normal bond away from the mirror, and then down, and then up, and then down. And describe the bond to this iodine here. Use the mirror as the reference. Is it going towards the mirror as you draw this bond, or away from the mirror? Away from the mirror and down. Not a wedge, not a dash, correct? So away from the mirror and down, not a wedge, not a dash. Right there. Go to carbon 5. This wedge is towards the mirror and down. Make sure your wedge is towards the mirror and down. Here, put the H on it. Dash is away from the mirror and down to the iodine. And congratulations. I'm just going to remind you that was R, and this was S. The mirror image of an S is an R. The mirror image of an R is an S. The second molecule is a lot less work than the first, isn't it? And you just got to believe me, if you drew the mirror image correctly, the mirror image of an R will be an S every time. You did. The pentagon's got a little better looking. These are towards the mirror, so this. Good. So we've done part B right here. This was A. And then C. C is a strategy for you. The best way to draw a third molecule is to copy your first molecule, except do a single switch on one of the stereocenters. You know what's going to happen to the stereocenter that you did a single switch on is going to be the opposite of what it was before you did the single switch. So I'll do the red one, and I'll do a single switch on the iodine and the hydrogen. And now it's going to be S, because that's what a single switch does. There's two ways to draw the other stereocenter. One, a mirror image way. We did that. Two, you can copy it as you see it, but just switch two of the groups. And that's also going to draw the opposite stereocenter. And I'm gonna leave the purple one as by itself because it doesn't say to do anything except for one stereocenter. All right, so I'm gonna copy everything as is. Why, I don't know. I'm gonna move that over just a hair, maybe. There, just lined up a little bit. The dash is not gonna have an iodine, and the wedge is not gonna have an H, because I did a switch. H and I switched. And the other stereocenter is identical to what it was before. Copy it as you see it. And what you have now is SS. SS. Yeah, makes sense. And then we're gonna draw the mirror image of part C. So I'm gonna make my mirror a little longer. Do the same thing I did, draw the other mirror image, start the same distance from the mirror. And the wedge is down towards the mirror. Going monochrome here all of a sudden. Up, down, I wedge towards mirror. H dash away from mirror. The mirror image of a red S is a red R. The mirror image of a purple S is a purple R. I didn't finish my molecule. What am I missing? The I. Thank you. Yeah. That's C and D. Oh, sorry about that. Oh, I don't have that. Don't have my drive in there at all? Oh no, the drive. I can't save it. I can save it on downloads, but that's dangerous. Because if I shut the computer off now, the file's gone. Yeah, I could. I leave it in downloads. Then email it to myself. Okay, beautiful. Compare each molecules. Well, I can tell you, you're going to get 2 points for saying you know that these are enantiomers. I'm going to connect these two. And I'm going to put a capital E. Yeah. And the same thing upstairs. E between these two. Yeah. They're definitely mirror images of each other. Yeah. These pairs, there's a pair there. There's a pair here. There's a pair here. And there's a pair there. Okay. So if you compare the orange and the orange or the gray, you'll notice in these two, the red one changed and the purple stayed the same. In these two, the purple one changed and the red stayed the same. In these two, the purple changed and the red stayed the same. And in these two, the red changed and the purple stayed the same. So I said the same thing 4 different times, didn't I? Something stayed the same and something changed. Okay? So some of the stereocenters change and some are different. If some of the stereocenters are different, but not all. What label did we put? We didn't put any label. It's not the it's not, oops, I almost gave the answer. It's not the E word, it's the D word, right? And what's the D word stand for? Diastereomer. Those are 6 quick points, those arrows. That's your 6 quickest points. Yeah. The two blue arrows represented mirror images. Those are enantiomers, but when some are different and some are not, it's called, I'm writing it right now, diastereomers. And you guys are gonna finish this. I didn't get the word all, but that's okay. If all of the stereocenters are different, if all of the stereocenters are different, then they're not called diastereomers. What are they called? Enantiomers. Can we verify that? In the pairs of enantiomers, look at the stereocenters, red and purple. If all of the stereocenters are different, some of the stereocenters are different, but not all diastereomers. And look, red was different and purple was different. What do you call those? Enantiomers. Red was different and purple was different. What do you call those? Enantiomers. Here, in all 4 other comparisons, one stayed the same and one changed. But I had to write it like this because, you know, some molecules have hundreds of stereocenters. So I got them all covered here. Okay. I think we should do another example just like this. Except our next example, we're only going to draw 3 molecules. We got to figure out why there was only 3, not 4. But anyway, we're not ready for that yet. Let's quit this one.